In this video, we're going to go over the composition of functions, specifically how to work with function composition and how to find the domain of a new function once you compose two previous ones. So let's just first start with the idea of what is a composition of functions. A composition of functions is an operation that you can do from two functions, and then you can compose them, which we'll talk about what that means in a second, and then that will give you a completely new function. So if we are going to evaluate a composition between functions first, there's a few ways you might see it. The way I'm going to use in the class, and the way I think you'll mostly see in the textbook, is where you have one function, the output variable, and then where the input variable would normally go, you've got another function being described. So it's like saying g of x, the function, is the input to the function f of x. And another way this could be written is f open circle g of x. In both cases, we would read this as the function f composed with the function g of x. So you always read from outside to inside, or f open circle composed with the function g of x. And what's happening is, notice as you read this function notation, you've got the function notation where f is the output value and g of x is the input value, but even within that, g is the output value at the input value x. So what's happening is the original input is x gets inputted into the function g, and we get the value g of x, and then the output of that g of x becomes the input for the function f. So what happens is we got the function x through the function g, and the output becomes g of x. But since g of x is the input to the function f, it's like we're inputting g of x, and the output is f of g of x. Now let's see what this looks like on a graph. So if we're looking at f of g of x is the entire input to the function f of x. Now I've got two graphs here. This first graph is the function g of x, and then I've got the function f of x. And what we want to graph is f of g of x, the composition of functions. So we know what happens first is x is the input. So we go over a fixed amount. For instance, let's let our x be a, and in the end, we want to consider what is f of g of a. So we look at the inside first. We've got to figure out what this is. And what's the input to this expression is a. So for the function g of x, we're going over a amount in the x-axis. And then notice we look visually vertically above and below, and we see it intersects the graph here, which is at the height g of a. So this is at height g of a, just saying it's the output value of the function g when the input is a. And then this g of a value, which is this fixed height here that I'm highlighting in yellow, whatever this y value is, that's what becomes the input to the function f of x. So we go over on the x-axis for the graph f of x, the distance g of a. So you can imagine this distance here is now the input to the function f of x. And you look vertically above and below, and you see it intersects the graph here. So what was the input to the function f of x? G of a. And that's why this output value is called f of g of a, because we had the input g of a and its corresponding output function in the function f. And the way you would graph this on the composite function is you would go over the original input, which was a, and the resulting output through this process was f of g of a. So that's kind of an idea of what happens whenever you graph a composition of functions. We did this for just one point a comma f of g of a, but you can imagine if you did this for all points in the domain of g of x, what would happen in the resulting f of g of x graph. And when you're reading through this, remember f g of x, this is not multiplication, this is composition. So we use the phrase f of, so the word of represents composition g of x. Now we saw what it looks like for functions to be composed graphically. Next, we're going to look at what it's like to look at function composition in a table. And then after that, in terms of function composition of equations, because we know every function can be expressed based on a graph, table, or equation. So in this table, we've got x values, f of x values, and g of x values. And probably we're more familiar with just a table with a clear input and a clear output. But this is a very efficient way to express for a fixed amount of input values the corresponding outputs for two different functions. So the way we would read this is if you go to the x value 2 and you wanted to know f of 2, then you would look in the f of x column down and we would see that's 4. But instead, if you wanted to know the value of g at 2, you would go over to the g of x column where those intersect and we'd see it's 5. So this is just an efficient way to show a function relationship between two different functions and the corresponding input values. So if we're looking at g of 2, the input is 2, but we're going over to the function g, so we know that's 5. And then when we evaluate the function composition f of g of 2, well, we first need to know, well, what is g of 2? From before, we found g of 2 is 5, which we could find again in the table if we needed to. So this could be simplified to be f of g of 2 is just the value 5. So now it's saying find the output value of f when the input takes on the value 5. So we go when x is 5, and we look, the f value is 6. Okay. Now for this next one, we see the difference is we've now got, the composition of g of the function f of negative 2. So notice the order of the composition is now switched. G is the outside function, and f of negative 2 is the input. So I recommend you would take a moment and pause the video, and actually why don't you complete number 3 and number 4, unpause to check your work. So as we look at this, we first realize our input that we need to consider is what is f of negative 2? So that means go to the input negative 2 and see the corresponding output value for f. So at negative 2, f of negative 2 is 0. So this could be simplified to be g of 0. Now we need to consider what is g of 0. So we look when the input is 0, what is the g value? And we see it is also 2. So the composition of function g of f of negative 2 is positive 2. Now our next one is, what is the composition f of g of 4? So our first point is we want to look at what is the input g of 4, simplify 2. So we would now go to when x is 4, the value of g is 0. So this simplifies to f of 0. Now we need to see, okay, what is f of 0? Looking at the table, we go to where the input is 0, but we go to the f value, and we would get 3 as our answer there. So this is how you can find the composition of functions given a table of values. Now, given two functions as equations, we can express the composition algebraically. So given f of t is the function t squared minus t, so what this function tells us is for any input we give it, it's going to square the input and then subtract the input from the square of the input. So it's like square the input and then subtract itself. And the function h of x, given an input x, it's going to say I'm going to multiply the input by 3 and then add 2. And we are asked to find h of f of t. So it's the composition of h of the function f of t. Now in this case, do we see f of t as the function written on the inside of the parentheses? That should tell us it's the input to the function h of x. So what we're going to do is everywhere there's an input for the function h of x, we are going to replace it with the entire input f of t, because that's what a composition means. Everywhere there would normally be an input, instead of having 3x plus 2, our input is no longer x. What is our input? F of t. So the whole value of f of t replaces the input in the expression if we're doing this function composition. So we would get 3 times t squared minus t plus 2. Now this can be simplified. 3t squared minus 3t plus 2. So the function h of f of t is equal to 3t squared minus 3t plus 2. Now, often if we reverse the order of the composition, we generally get a different resulting function. Not all the times, but most times it would be different, and we'll talk about more of that in a future section. But for practice, why don't you calculate f of h of x based on our equation for f of t and h of x. At this point, I recommend you would pause the video, write out your resulting function composition, unpause to check your work. So in this case, h of x is the input to the function f of t. And what does f of t do to the input? It squares it and then subtracts it, but instead of t, we now have the entire function 3x plus 2. So f of h of x equals the whole input 3x plus 2 squared minus itself. So that would be our function f of h of x. Now this can be simplified if we wish. Squaring this binomial, it would be the same as foiling it. If it helps to write it out to help you see the FOIL, feel free to do that. You could also mentally think through the formula. Now when we are subtracting a multi-term, the subtraction goes to both terms. So we'd say minus 3x minus 2. I'm going to FOIL this. (9x squared) plus 6x plus 6x plus 4. That we're then subtracting 3x and subtracting 2. So we get this is equal to 9x squared. That would be 12x together. That we're then subtracting 3x, so we get a minus 9x. And then we've got a plus 4, and minus 2 would give us a plus 2. And that's our h of f of x, or sorry, f of h of x. And notice, based on the order that we did the composition, we got significantly different results. Now in a previous section, we talked about how to find the domain of a function composition. Sorry, in a previous video, we talked about how to find the domain of just a general function. And that's going to be important to review. If you're unfamiliar with that process yet, I recommend before you finish watching this video, you would go back to that section, 1.2, and do all the homework problems from there. Seek help in office hours if needed. Email me questions. And then once you're confident with finding just the domain of a general function, then we can talk about the additional step of finding the domain of a function composition. So finding the domain of f of g of x can be simplified into these 3 steps. First, you need to find the domain of the inside function. In this case, the inside function is g of x by how it's written here, but we might leave it more general based on your future example. So find the domain of the inside function is step 1. If there are any restrictions, keep them and maybe box them so you can find it later. Then you construct the composite function. Find the domain of this new function, and we will have simplified as much as possible there. And then finally, after you have found the domain of the inside, simplified the resulting composite function, if there is overlap between the 2 restrictions that you found, use the more restrictive domain. And it's important to note that the domain of the composite function may be unrelated to the domains of the original functions. So let's look at our first example. Suppose for the composite function f of g of x, the domain of g of x is all the x values where x cannot equal 2. So it's okay anywhere except where x equals 2. And the domain of the new function after composition, I'm going to change the colors here to be consistent to our steps 1, 2, and 3. The domain of the new function that we formed after composing is all values where x is greater than 0. So notice this example is just kind of doing steps 1 and 2 for us. It's just giving us the information we've got to interpret it. So step 1 told us that the domain of g of x was anything except 2. You were okay anywhere except 2. And then we found in step 2 that if you form the composition f of g of x, its domain was all values greater than 0. Now we're asked to find the domain of f of g of x. And what I'd recommend doing here is after you get step 1 and step 2, maybe you draw a corresponding number line for each one, and then you just correspond what must be true in both to get my more restrictive domain for all 3. So for the first one, if you just can't be equal to 2, you can't be at 2, but you could be before 2 and after 2. And if you've got to be greater than 0, notice how my 0 is to the left of 2 as it normally would be. I think that helps visualize. So I'm kind of stacking them. 0 should come to the left of the 2, even though these are separate intervals. 0 has to be greater than 0, so we can't be equal to 0. We can't be less than 0, but we can be greater than 0. Now we need to combine both of these restrictions to get our overall domain of the composition by saying, where is it true for both? So do we see the key points of interest seem to be at 0 and 2 from our 2 number lines? So I'm going to plot those. And I'm just going to go piece at a time left to right and say, if it's okay in both, it's okay in the final. If it fails for any point in either one, it fails in the final. So our first section, if we're looking at this overall graph, do we agree we've got everything before 0, at 0, between 0 and 2, at 2, after 2. So I kind of see this as 1, 2, 3, 4, 5 sections that I need to think about. So the section first, as we go from negative infinity all the way to 0, is all the negative numbers. Now notice it was okay to be negative here. We got the check mark, but it was not okay to be negative here. So since it failed for either of them, it's failed for the combining one, right? It's got to be okay in both. And now as we go at 0, notice it's not okay at 0 in this one, so it definitely can't be okay in the final. The next section is between 0 and 2. Notice 0 would be here on the first graph, so it was okay between 0 and 2 in the first graph. And isn't 2 here? It's okay between 0 and 2 in the second graph, right? You just had to be greater than 0. So this was x couldn't be 0, or sorry, couldn't be 2. Here x had to be greater than 0. So we can be between 0 and 2, but notice we cannot equal 2 exactly. And then can we be greater than 2? Yes and yes, since they both agree. We've got that. And now if we just wanted to, this is the domain, but if we wanted to write the domain in interval notation, we would say it's everything between 0 and 2, not including either. So open parentheses 0 to 2. Union is when you've got kind of multiple things that you're linking together. After 2 to infinity, right? Because it continues out here forever. So union open parenthesis, because we're not including the 2, to positive infinity would be the domain of the resulting composition. Now in this next example, we're given 2 functions, f of x and g of x, and we're asked to find the domain of their composite function. So we'd want to remember the steps that we just discussed. First, you need to identify in this composite which is the inside function. Take a moment to think about which is the inside function. Here, f of x is the inside function, so step 1 said find the domain of the inside, which for us, the domain of the inside function is the domain of f of x. So we need to think, what is this domain? Now this is similar to what we did back in 1.2 notes, so why don't you take a moment to think about what is the domain of the square root of x minus 10? To give yourself adequate time, pause the video now, Write out the domain of f of x here. Unpause to check your work. We look at this function, and basically it's just the square root, right? That's all its structure is. All we know is that the inside of square roots can't be negative, because the square root of a negative number is not a real number. So we know that x minus 10, whatever it is, it better be positive or equal to 0. Either is fine, right? You can have the square root of 0, that's just 0. Square root of a positive number, some positive number. It's only the square root of negative numbers that gives us issues. So when we solve this, we get the simple inequality x better be greater than or equal to 10, which if I want to help me out, I might just draw my number line while I'm at it. So 10, could we be equal to 10? Yes, because you could be greater than or equal to. We could be bigger than 10, but we shouldn't be smaller than 10. Now step 2 is form the composition, and then simplify it and think about its domain. So why don't you take a moment to form the composition, get a resulting function, and then think about its domain. I recommend you pause the video again at this time to complete step 2. Unpause to check your work. Now here we see f of x is our inside function. So this whole f of x is going inside where the normal input for g of x is. What does g of x do to inputs? It squares them. So g of x normally squares. What's it squaring? The square root of x minus 10. Squaring a square root, just the exponents become the exponent 1. You can imagine them canceling out. What's really happening is we're just left with the exponent 1, which we normally don't write. And this resulting function x minus 10 is just a straight line. Okay, it has no domain restrictions. Its domain is everything. We also know that because it's a polynomial, the domain is everything, so its domain is negative infinity to infinity. And if you were to show that on a number line, everything would be okay. Now step 3 is to say, okay, I realize that we've got two domain things to consider. We need to look at when they're both true. So if you would pause the video again and draw your number line that shows when are they both true, when are both of these conditions met. Remember, if it fails for one, it fails for all. Pause, unpause to check your work later. As I'm thinking of drawing this number line, I look at the points of interest. For the first graph, we had to care about what was happening about 10, but for the second graph, everything was fine. So let's think, before 10, were we okay? No, because it wasn't okay in one of them. Were we okay at 10? We were okay for the first one, and then this one was okay with everybody, so it was okay here, of course, too. So 10 is okay. Were we okay after 10? Well, we were okay here, and then this was okay with everyone, so it's okay here. That means the domain of g of f of x was everything including 10, because we could be equal to 10, out to positive infinity. And that would be our answer for this equation, because we could be equal to 10 and then greater than 10. Now we've got another example here for the function f of x is 1 over x, and the function g of x, which is 1 over the x minus 2 multiplied by x plus 4 in the denominator. Find the domain of the composition. Remember, step 1 of finding the domain of a composition is to find the domain of the inside function. So remember your step 1, find the domain of the inside function. Which is the inside function based on the notation? Identify that for yourself. F of x is inside the parentheses, right? So it's the inside function. So the first step is to find the domain of inside function, which for us is f of x. Okay, take a moment to pause the video and write out the domain of 1 over x, both in a number line and an interval notation. We know that 1 over x, the structure is just a fraction, right? The top is always okay. But the bottom of a fraction always has trouble when the bottom of the fraction would be equal to 0. So we do not want it to be equal to 0. But in this case, the bottom of the fraction is so simple, it just boils down to don't let x be equal to 0. It's fine for any other x value. So in terms of a number line, the only point of interest is x. It can't be that, but it could be everything before. It could be everything after. So we've got the interval notation negative infinity to 0, open parenthesis, 0 to infinity. Now step 2 is to form the composition. So form the composition, form g of f of x on your paper, and then think about its resulting domain. So pause the video, find g of f of x, simplify, and find its domain. After you've done that, unpause to check your work. So in this case, our inside function is f of x, and f of x is 1 over x. Now, where is it being placed? It's being placed as the inside of g of x. So it's like it's replacing the x. Instead of the x, it's now 1 over x in the function. So g of f of x is saying for every input in the normal function g of x, we are now replacing it with f of x, or 1 over x. So we've got 1 over and now we need to simplify this. Now at this point, if we would expand this out, I don't think it's going to simplify much, because a lot of times when you're trying to solve things, you would have to factor again, because specifically, what are we curious about? We're curious about this domain. Well, we know this domain. Overall, do we agree this structure is a fraction? Something divided by something? Fractions only have trouble when the bottom is 0. So we need to make sure that 1 over x minus 2 times 1 over x plus 4, that can't equal 0. Now 1 never has trouble, and specifically, what do we know about this expression is within 1 over x can't be 0, but that was already covered here. So if we can just find where this would avoid us being, then we can combine everything together for our step 3. Now remember, if this can't equal 0, that means the separate pieces can't equal 0, because the only way a product equals 0 is if one of the pieces equals 0, so that when they multiply, it cancels everything out. So we need to solve this equation. We do not want this to equal 0. We also need to solve this equation. We do not want this to equal 0. Let's add 2 to both sides here, and we would get 1 over x cannot equal 2. Maybe to solve for this, we would multiply both sides by x. That cancels, and you're just left with 1 on this side, cannot be 2x. Divide both sides by 2, and we get x cannot equal 1/2 for this one. Pause the video and solve the other inequality. Here we would subtract 4 from both sides, and we get 1 over x cannot equal -4. Multiply both sides by x, and we get 1 cannot equal -4x. That tells us x cannot equal -1/4. So we've got these two restrictions, and if we were looking at that in the domain, because the whole bottom can't equal 0, x can't be 1/2 or -1/4. But also within the expression itself, do we see that we would have a problem if x was 0? Because then within the expression you'd have 1 over 0, which is a problem. So we also can't have 0. So we know we can't be equal to -1/4, we can't be equal to 0, but we were okay everywhere else. These were our only restrictions. So step 3 is to combine it all together, but we've kind of already combined everything. We just need to think about, okay, here's our 2 inequalities from steps 1 and steps 2, our number lines. How would we make that into our final number line? What are the points of interest? -1/4, 0, and 2. Take a moment to pause the video and fill in checks in X, where is everything okay, the resulting interval notation. Unpause to check your work for your final answer to this example. So here we've kind of got 1, 2, 3, 4, 5, 6. I can see 7 sections, right? Everything before -1/4, at -1/4, between -1/4 and 0, at 0, between 0 and 2, at 2, after 2. And looking at each of these 7 locations, or intervals or places, we know that before -1/4 is here for the first one, here for the first one, they both agree there. Now this one said you can't be -1/4. It also said you can't be 0, and you can't be 1/2. We might as well fill that in. Sorry, that was 1/2, not 2. And then could we be between -1/4 and 0? Well, -1/4 is like here. And it said, yeah, you just had to be not 0 for the first one. And we could be between -1/4 and 0 here. We had that check mark. Now, could we be between 0 and 1/2? Yes for here, and yes for here, because here's 1/2. We are okay so long as we're not 0. And then we could be bigger than 1/2 and bigger than 1/2. So the overall domain of g of f of x in interval notation is starting everything from -infinity up to -1/2, open parentheses, or sorry, -1/4, union, starting again at -1/4 and going all the way to 0, but open parentheses, union, 0 to 1/2, open parentheses, union 1/2 to infinity. And this would be our final answer for this problem. Okay. Now, this problem, this next one, is similar in content. It's finding the domain of a composition, which we've been doing repeatedly. But specifically, the functions involved, when you compose them, in the end, you're going to have to solve a rational inequality. And what I'll say is solving something involving a rational inequality would not be on an upcoming quiz or exam. Now, any of our previous problems or ones in similar difficulty level totally could come up on quizzes or exams. All I'm eliminating is specifically those that involve rational inequalities, but it still could be a useful process to have seen and know. So this is going to be a PDF that I'm going to solve the problem and explain it, and I'm going to upload that to Canvas later this week. But it is optional, since we're not going to be tested over finding the domain of a function composition involving a rational inequality. But if you're interested in seeing maybe finding the domain of a composition of an even more complicated function, this would definitely be something that you'd want to look at. So again, all the previous problems, everything of similar difficulty, will be on a quiz or exam. But specifically what I'm eliminating is those function compositions that create a rational inequality. You don't need to worry about what they are. If it's assigned, you can do it. I'm just saying one of this difficulty won't be on a future quiz or exam. So if you have questions about this, send me an email. I'll be happy to clarify. And if you are interested in this problem, then look for the upcoming PDF that will be uploaded to Canvas later this week.